So we start with this next lecture of these memory elements that we are studying. And after the latches, so we ended the latches with an idea of control input, and we are talking about the concept of synchronizing the output changes in the output with the changes in the control input. And when we will be able to achieve that, then the same circuit that we saw for the latches, that will call as flip-flops. The same circuit, when it is asynchronous in nature, we call it latch. When it is synchronous in nature, we call it flip-flop. And how we make it synchronous, that is what we will investigate here. Before that, one needs to understand two concepts. Two concepts on how the clock input will be able to trigger the change in the output. The clock input will be able to trigger the change in the output in two fashions. One is level triggered, another is edge triggered. So when we are operating in the level triggered mode, then the SR input will affect the output whenever the clock is maintaining some level. Either it can be high or it can be low. So level trigger can be active high trigger or active low trigger. So whatever be it, suppose for our ease of understanding, active high level trigger, that means when the clock is high or the clock is 1, that time if I change my SR input, the output will change. This is level triggered. This can happen also for active low, that means when the clock is 0 and I change my SR input, then the output will change. The control is asynchronous here because the change of the output is not depending on the clock inputs changes. When we are changing our mode of operation to edge triggered, then the SR input will affect the output only when the clock is changing levels, either low to high or high to low. When it is changing level from low to high, we call it positive edge trigger. When it is changing level from high to low, we call it negative edge trigger. So you are try to understand the concept of positive edge and negative edge. This is the positive edge. It is changing from low to high. This is the positive edge. When it is changing from high to low, this is the negative edge. So for any pulse, first the positive edge comes, then the negative edge comes. So we understand what is the positive edge and what is the negative edge, and what we are saying here, that no matter what the S and R inputs are, the output will not change unless there is an edge trigger. So at the edge, then it will look at what S and R combination is, and accordingly it will change the output. The output will of course get changed based on what S and R inputs are. However, it will change at the instant of the clock edge trigger. It will not change otherwise. So if it is positive edge trigger, it will change at the instant of clock going from low to high, and if it is negative edge trigger, it will change, the output will change at the instant of clock going from high to low. In this situation, the control becomes synchronous because the output is changing at the instant of the change in the control input also. At a particular instant, the output is changing, and that particular instant is very much known to us. That is the instant of the edge trigger, either positive or negative. So this is how we can actually make the circuit behave in a synchronous manner, and when we will do that, we will get flip-flops. Now the question will come, how we are actually making the edge trigger, because we know that any gate, because ultimately these are gates, right? whatever the latch circuit was, they were gates. The gate does not function at a trigger, at a pulse trigger. It functions when there is a definite input 1 or 0 at the input side. So the gate would function only when there is a definite high and low input values at the input side, then it will give out an output which is also high or low. So this positive edge and negative edge trigger is basically a very short duration pulse, short duration rectangular pulse. That means it will have either a high or a low. Okay, so let us try to create a positive edge trigger and a negative edge trigger, and the ultimate trigger being a high pulse here. Okay, so you see here we supply the clock signal like this to the input of AND gate. In one input we supply the clock signal as it is, in another input we invert the clock signal by odd number of times. That means here it is inverted and it is also shifted a bit. Shifting happens because it passes through some gate delays, not gate delays. So it is inverted but it is also shifted. Now if you do an AND operation with this, you will get a high pulse at this particular, between these two particular time frames, the dotted lines that you are seeing. And hence you can see when the clock is transitioning from low to high, at that instant we are getting a very short duration high pulse. So this is a positive edge trigger where the ultimate trigger is high in nature. What is a negative edge trigger? When the clock, here we are constructing a negative edge trigger like this using a NOR gate. In the same fashion we are passing A and B, you see. So B is shifted and inverted, and now the NOR operation will generate a high signal only when both the inputs are low. And you see in this total duration, when the both signals are low at this instant, between these two dotted line window, and you see this starts at the negative edge trigger, at the negative edge. So when the A falls from high to low, there is a high pulse at the output. Okay, now one may ask you to make a circuit where the final pulse would be a low pulse. That means it will be like this. Okay, by like this. So in inversion of this y, inversion of this y. So it is very simple. Here if you have basically a NOT gate, that means you make a NAND gate instead of AND gate, you will get that particular type of pulse. And in this case, if instead of the NOR gate you simply have an OR gate, you will get that type of pulse. Okay, so that is how to create the positive edge trigger and the negative edge trigger. And now we know that we are actually not, when we are talking about edge triggering, we are not supplying the clock directly, but we are supplying the clock through some circuit like this, which makes the trigger. Okay, it makes that edge trigger. So with that idea in our mind, now we look at the circuit again. And here this clock is not the clock directly, but passing through some edge triggering circuit. Hence, what we will get as the operation of this circuit would be same as what operation we studied before, but the enable will change to edge trigger. The enable high and low will change to edge trigger. Now suppose that this clock passes through a positive edge triggering circuit, then the truth table will be reformulated like this, where the change in the output due to SNR will happen only at positive edge triggers of the clock. At any other instant of the clock, whether it be level high, level low, or negative edge trigger, S and R input changes will not affect the output. It will be memory. So the clock, when it is positive edge triggered, only then the input side will change. And hence this operation becomes synchronized. This operation becomes synchronized with the change in the clock signal, and hence it is called synchronous operation, and this circuit is called a flip-flop. It is no more called a latch, it is called a flip-flop now. A block diagram notation of the flip-flop is like this, where this triangle indicates that it is edge triggered. If there is no triangle, then it indicates it is level triggered. So this is S, this is R, and this is the control input. If this triangle is there, it indicates it is edge triggered and positively edge triggered. If there is a bubble in front of this triangle, it indicates it is negative edge triggered. Negative edge triggered. Sometimes we also write the block diagram like this. Instead of writing Q bar, we simply write a bubble at the exit point of this second output. The truth table for all these symbologies and this circuit remains this. Okay. So now from the truth table of, so here we are maintaining a positive edge trigger. However, we just need to know which edge trigger it is, and if we know that, then this column does not make any further contribution to our information or to our knowledge. Once we know whether it is positive edge trigger or negative edge trigger, then we can simply delete this column and we can start looking into these 4 columns. Okay, this is what is important. So this is the truth table. From the truth table we can construct something called the characteristic table. The characteristic table, the input and the output you note in the characteristic table. The input is the present output and the present inputs S and R. The output of the characteristic table is the next output, the future output. Sometimes we write as Qn plus 1 also. Sometimes we write as Q plus also. Both are fine. So Qn plus 1. So now we have 8 configurations because there are 3 inputs, and now we have to check for each particular configuration. We have to look back into the truth table and see what my next output would be. So like here, you know that S equals to R, S equals to 0, R equals to 0 will always give you the memory. So whatever your, so from here truth table, you know it will give you a memory. Q plus is Q. So Qn plus 1, what would be? It will be Qn. So Qn is 0, Qn plus 1 is also 0. So in this way you can form the characteristic table from the knowledge of the truth table. And you look at any of these rows randomly. Let us select this. So this is X. Let us see what is happening here. X means it is not used basically, because this 1 1 configuration, we know that this configuration is not used. Okay, so no matter what is your Qn, that time it will not give anything here because you are not using this. So this particular set is not valid, not a valid row actually. Okay, so this is denoted by cross. And then in other rows, any other row you see that let us see this row, so 0 1. So whenever you have 0 1, the output will become 0. So output becomes 0 no matter what your output was. So output was 1, but it will become 0 because the input is 0 and 1. Here also you see is 0 and 1, output becomes 0 no matter what is the input. The input here incidentally was also, the output here incidentally was also 0, but the output becomes 0 because of S and R being 0. In this way you can form the characteristic table. Once you make the characteristic table, you can further make something called the excitation table. Okay, so this is the excitation table. Here the input are Qn and Qn plus 1, which are basically the present output and the next output, and the outputs of this excitation table are the inputs S and R. How do you read this? You have to read it in this way, that if I observe a certain output and I want my next state output to be something, then what are the inputs I must give to the flip flop? This is what you are trying to read from the excitation table. It is giving you the excitation that you are supposed to give to the flip flop in order to change the output from a given output to another given output. So for this, you basically have to look into the characteristic table. So you have a 0, you want to go to 0. You see that when you have a 0 here and you want to go to a 0 here, so at the inputs Qn, when Qn is 0, you see at that condition when Qn plus 1 is also 0. Qn plus 1 is 0 at these two particular conditions, and this two particular condition, S has to be 0, R can be either 0 or 1, does not matter. You see, S is 0, R is don't care. Okay, here 0 to 1, if you are at 0 and you want to go to 1, then you look at here 0 and you want to go to 1, so you have to give the input combination as 1 0 1 0. Similarly, you read the other two lines also, 1 0. So when you are 1 and you want to go to 0, so this is the only possible combination. So you have to give input S and R as 0 and 1. When you are at 1, you want to go to 1, so these two rows are valid. So you can either give S and R as 0 0 or you can give as 1 0. So S is don't care and R is 0. From the characteristic table, there is something called the characteristic equation that you can formulate. The characteristic equation basically gives the next state depending on the present state and the present inputs. So it is a function of the present states and the present input. So you have to find out Qn plus 1 based on S, R and Qn. So you have basically a table you have in front of you and you have to solve for the expression. So you go via the usual route that we have already studied, which is the route of the K-map. So with the help of the K-map, you will be able to ascertain that Qn plus 1 would be basically S or Qn and R naught. So you can try to figure this out, and this is already very well known, and you will be also able to solve this using the characteristic table. So this is the characteristic equation of the SR flip-flop. So the characteristic, there is a characteristic table, excitation table and characteristic equation of a flip-flop, and these are these characteristic table, excitation table and the characteristic equation of the SR flip-flop. There are other flip-flops also one can make starting from the SR flip-flop. SR flip-flop is the very basic, okay, the very foundation of the various memory elements. There is another memory element which is the D flip-flop. Here what we do, we connect the S and R inputs together via a NOT gate. So the D input you see directly goes to S but goes to R through a NOT gate. That means when D is 0, your input combination to the SR flip-flop is 0 1. When D is 1, the S and R are 1 and 0. So what does it do? Here the input states are only two, 0 and 1, D being 0 and 1, and the output, as you can see, will also be 0 and 1. When D is 0, output will also be 0. When D is 1, output is also 1. Remember the SR flip-flop truth table. What we have achieved here, we have achieved the there is no possibility of the invalid case. So that restricted use, that 1 we will not use, it is invalid, we have to always tell the user not to use the 1 input. That situation is removed now. We don't need to bother about the invalid case. The invalid case will not appear in this configuration. Here the output will simply change depending on the input, and when you don't want the input to change, you simply make the control input like maintain it as high or low or something like that. So you disable the flip-flop, then your output will remain as memory. So this is the way the D flip-flop works, and D flip-flop is very important, very easy and very useful also. We will find the use of this later on when we are making sequential circuit designs. It is also having a characteristic table and a characteristic equation and an excitation table, and I have simply put them here. You will be able to formulate this characteristic table and the excitation table very easily by looking into the truth table. They are very easy. D flip-flop. So next I will come to the JK flip-flop, and in the JK flip-flop we are having the SR flip-flop like this. Additionally, we are having the NAND gates. We are having 3 input NAND gates at the input side of the SR flip-flop. Okay, so this is the SR latch. This is the basic SR latch. And if you remember the basic SR latch truth table, we have again written down it here. And based on this, we will now evaluate what is the truth table of the JK flip-flop, where J and K are the inputs like this. Okay. And you see additional inputs to this NAND gate. Which are the additional inputs? This clock input, and the outputs are fed back. The Q bar output is fed back to the J NAND, and the Q output is fed back to the K NAND gate. This is the JK flip-flop. So now let us see here. Since we are dealing with, suppose we are dealing with positive edge trigger, so obviously when other conditions are there, it is memory state, and when we have positive edge trigger but J and K is 0, J and K 0 means S and R would be 1 1, and that is the memory state. That is fine. But what about the configuration 0 1 1 0 and 1 1? So we have to investigate that. Now let us start with 0 1. So when your J is 0, of course S is 1, right? And let us see. So like this. So when we are having 0 1, we are trying to look into 2 possible situations of the output. So when Q is 1 and Q bar is 0, there is a case 1. So at that time, what would be your R and S? Let us see. So when J is 0, obviously S will become 1. S will become 1. What is happening to R? Now R is getting formed by this clock is enabling this NAND gate. Then this K is 1 and your Q is also 1. K and Q both are 1. So the R will become 0. So R is 0. So S is 1, R is 0. And from the truth table, you see that your output would be 0 1, Q0 and Q bar 1. However, we also need to be satisfied that this output will be 0 and 1 even when we start from Q as 0 and Q bar as 1. So Q, the J being 0, this is 1 anyway, okay, but now Q is 0, K is 0. So here what happens, your R becomes 1. Now the input configuration of S and R is 1 1, and you have the memory state. And what is the memory state? The same 0 and 1 will then remain at the output. That means no matter what the output is, whether it is 1 0 or 0 1, if you give jk as 0 1, your output will become 0 and 1. Okay. Similarly, let us now analyze the input configuration 1 0. Now k being 0, R becomes 1 directly, and doing the same sort of analysis for Q0 Q bar 1, the Q bar is 1, so now you have a 1 here, 1 here, so S is basically 0 now, and hence you will have S equals to 0, R equals to 1, output is 1 0. When you start with the output as 1 0, then you will get R equals to 1, R equals to 1 is because K equals to 0. Now J equals to 1, Q bar is 0, so S will become 1. So 1 1 configuration is the memory configuration, so your output will remain 1 0. So no matter what your output was, this or this, when you are giving input as 0 1 0, you are getting output as 1. So that is fine. So we have got jk 0 1 output 0 1, jk 1 0 output 0 1 0. So this is same as SR flip flop. Nothing additional we are achieving. But what additional we are achieving? Why we are going to jk flip flop? Because we want to utilize this state, which we are not able to utilize in the SR flip flop. So what happens here? Let us see. When we are giving 1 1, jk is 1 1, okay. So now your q is 0, q bar is 1. Let us suppose we start from q0 and q bar 1. Then jk is 1 1, so this NAND gate is getting actually influenced by the outputs. So q is 0, so R will become 1, q bar is 1, so S will become 0, right? And when this is the configuration, you see the output would be 1 0. Now if you start from the output 1 0, then since this is 1, this will become 0, and since this is 0, this will become 1. So that is the situation. R equals to 0, S equals to 1, and that will give you the output as 0 and 1. Now you notice what happens when you start from 0 1, you make the output 1 0. When you start from 1 0, you make the output 0 1. That means the output complements. So the next state is a complement of the present state. So the output as if toggles. So it is called the toggle state actually. This is called the toggle state, and we write down the truth table in this manner. Sometimes we don't write the q bar because it is simply the reciprocal of q. So we simply write this. This is a toggle state which is represented by q bar. So when you are giving 1 1 to jk input, you are getting the toggle state. So what does it mean? Whatever the input, whatever the output was, it is getting complemented. So you are achieving another state, not simply 0 1 and memory, but you are also achieving a state called the toggle state using the jk flip flop. Now you look into the characteristic table, excitation table, and the characteristic equation. Same way, you have to form the characteristic table by looking into the truth table, and You have to form the excitation table by looking into the characteristic table, and I leave it up to you to verify that this characteristic table and excitation table are fine, and you construct these tables starting from the truth table which I have explained right now. When we have the characteristic table, then you can form the characteristic equation, and the equation will be like this. So this is a very well known characteristic equation of the JK flip flop. Qn plus 1 is Qn bar J plus Qn K bar. So that is a characteristic equation of the JK flip flop. Now there is a condition. This is very important in JK flip flop. So this condition happens when you have you don't have a edge trigger. When you don't have a edge triggered flip flop, so that means it is like a latch, or suppose the edge trigger is also like a pulse, right? So there is some duration of the clock being high. So during that situation, what happens? When I have my input as 1 1 all through that pulse duration, so my output will keep changing always. It will become 1, it will then become 0, it will become again 1, it will become 0, and like that it will keep toggling as long as my clock is high, or it is acting like an enable. Okay, so this is how the situation will become. So you have given JK as high, both are high, and now whenever the clock is activating the flip flop, so this is a very short duration, but still some duration is there, right? And it may be, if you are level triggering, then it is a long duration. So whatever be that, you are always having these short pulses now. So this is the toggling which keeps on happening. When the clock becomes low, then no more toggle. Okay, it maintains the state. This is a memory now. But again, as it becomes high, again a toggling happens. This situation is called the race around condition. Race around condition, because the output is as if racing, and it is very quickly changing. Very fast change happens, and this actually has a possibility of damaging the circuit. This race around condition must be avoided. That means the JK flip flop must be connected in such a way that we are able to overcome the racing, and one such way is to maintain a clock signal's time period as less than the flip flop delay. This should not be t by 2, this should be the t on time. Okay, it's t on. So considering we have obviously this circuit activates when your clock is high, so t on must be less than flip flop delay. Or, so here I have changed, but this slide I have not changed. So this is the right thing. So t on is less than flip flop delay, or we have edge triggering, or we have edge triggering, or we have a master slave configuration. This is also a valid thing that we can do, and this is actually what we will do. Why? Because we are not very certain about these two conditions. What is the flip flop delay? We don't really know. Are we able to keep the t on less than flip flop delay? Not very certain. Okay. Edge triggering, we are constructing the edge trigger pulses. What is the width of those pulses? We are not very certain about it. So this is not very certain. But when we are using master slave configuration, we would be certainly getting edge triggered behavior. We will be certainly getting edge triggered behavior of the JK flip flop, and the rest around condition will be completely avoided. How to do that? That I think we will see next lecture. That master slave configuration we will see in the next lecture, but we will complete the set of flip flops with introducing another flip flop, which is the T flip flop or the toggle flip flop. In the T flip flop, we are simply connecting the J and K together. J and K we are tying up together, and we are denoting this signal as T. So now this becomes a T flip. Now you see, when you are giving 0, then J and K is 0, so it is acts as a memory. And when you are giving T as 1, your J and K both are 1, and it acts as a toggle. So either you have a memory state or you have a toggle state. These are the two possibilities. So whatever you are having, you will remain there unless you are trying to change it. And when you are trying to change it, you give a toggle signal high, it will change. So this is the toggle flip flop or the T flip flop. There are two very important asynchronous inputs to the flip flops, which are called the preset and clear. And the function of these asynchronous inputs to a flip flop is to change the output at any instant if there is a need. Because you know that in the flip flop, the S and R is not able to influence the output unless there is a edge trigger. Okay, so we need some way to influence the output if there is a need, no matter what the clock is. So no matter whether the clock is high or low or positive edge or negative edge, it doesn't matter. We want to directly affect the outputs if it is required, and for that we need some asynchronous inputs. This preset and clear are the asynchronous inputs, and normally they are active low type. This particular configuration with the NAND gates demand that they be active low type. Here, if you have this preset bar, because it is active low, as 0, then you can understand that Q will become 1 directly. Q will become 1, and clear, this being 1, this NAND gate acts according to the other signals. Okay, so this will become 1 and this will become 0, because this being 1 according to other circuitry makes this 0, and preset being 1 and clear being 0 will reset the output. Clear being 0 makes this 1, and hence this becomes 0. So this is the conditions for setting and resetting the output. Preset, since these are active low, so you have to activate the preset by making this signal as low, and hence it will set the output. You are giving the preset as low, but it is making the output high. It is setting the output. You are making the clear signal 0, and it is resetting the output. It is making the output 0. When preset and clear both are 1, then you are deactivating the preset and clear signal. Basically, you are deactivating these controls, and the flip flop will perform its normal operation. So when this is 1 and this is 1, then the rest of the circuitry remains like a flip flop, normal flip flop operation, and hence these are not affecting the output in any way. So it is deactivating the preset and clear, and normal flip flop operation will continue. If preset and clear are both 0, then there is a problem. It is not allowed. So you must not give preset and clear both 0. You should not try to activate both at the same time, because it will be confused, because it will try to set 1 here, both 1, and both 1 will confuse the circuit, because it will lead to some unstable conditions. It may damage the flip flop. So This is important because when you will do experiments, when you will actually work with flip-flops, you will find there is a preset and clear signal which you need to basically give some high or low something there. So basically we initiate the flip-flop maybe with a high and low. So we give preset as 0, clear as 1, and this flip-flop will be set 1 and 0, and then we will make both 1, because now we will deactivate these controls and we will try to observe the normal flip-flop operation. This input will never use. The preset 0 and clear, this is never to be used. So that is all about flip-flops in general, and next lecture we will learn about the master-slave configuration, which is very important to understand. Thank you for your attention. See you in the next lecture.